Following on from the previous video, our aim is to find out the gradient of this function at a here. And we started out by having b to be around here, and then we slowly move b towards a. And at the end of the previous video, we got to this stage here. So suppose b is here, then this bit here will be given by this. And then we have to divide. Well, for us to find out the gradient of this line here, we would get the height here. We would get this height, which is this bit here, and then divided by this distance here, the base here, which is h here. So so the gradient of this thing is really this divided by this length here. Okay, and then as we move b to closer and closer to a. Let's say b is, let's say b is here. Okay. Well, even though b is here, the gradient of this line here is still given by this formula here. It's still the same. Look at the previous one. The previous one, the formula is still the same. It's always f of x plus h. Take away the original starting point here, and then divided by h here, the length here. That will give you the gradient of this line here. But the thing is, as you move b closer and closer, even if b is around here, the formula still stays the same. Look at this formula here. Okay. Now let's look at the suppose b is here. Okay. See, the formula is still the same. The formula is still the same. And then as remember, the way we move b towards a is us decreasing this h. You see, by decreasing the h, b it gives the effect that b is moving towards a. So us moving b towards a is really us making h smaller and smaller each time. So hang on, let me start again. So originally we were here, and then so h is quite big here. H is quite big. Now slowly decrease h. So now it's at this stage, and then decrease h again, and it will take you to this stage here. Again, the formula for this line is given by this, exactly the same as before. But you see, the closer we make h, the more accurate the gradient will be. You see, if you make h to be really small, let's say 0.00001, then it becomes more accurate. The smaller h is, the more accurate it will become. But here's the thing: you can't make h to be 0, because if you look at this here, if you make h to be 0, then you're going to have well, this thing here will be well, x plus h will be x, but this thing here will be something over 0, because h is 0. You've got a case where if you make h equals 0 here, looking at the gradient, if you make h to be 0, then you've got pretty much, well, x plus h is 0, so f of x, and if you make h 0, then it would be f of x, take away this thing here, which is f of x, and then you divide it by 0. So here you've got same thing, take away the same thing. So in effect, you've got 0 over 0, which is meaningless. And in our graph scenario, if you make h to be 0, it's like you having a remember, to work out the gradient, we need a triangle. If you make h to be 0, it's like you having no triangle. It's just you having one dot. So you don't really have a triangle in order to work out the gradient. So it's meaningless to have h to be 0, but you can have h to be really small. And the thing is, the smaller you make h, the more accurate the gradient will become. Well, from our knowledge of limits, if we ultimately want h to be really small, we want h to head towards 0. We want the limit of h to be, well, we want h to head towards 0. So if we want to know the true gradient at a, we're going to have to do this. Take the limit of this here. Hang on, this here plus h. Just get the formula for the gradient. Okay, over h, but get h to head towards 0. So take the limit as h tends to 0. And remember that down on 0, this whole thing here is meaningless. But we can take the limit as meaning that make h to get h to be really small. Well, take the limit. So the gradient is really the limit of this thing here. Okay.